Hello students, in this video lecture we will summarize chapter number 5, that is laws of motion, which is given in physics for class 11. It will cover topics like Aristotle's fallacy, the law of inertia, Newton's first law, second law and third law, conservation of momentum, equilibrium of a particle, common forces in mechanics, circular motion and solving problems in mechanics. We will solve remaining numerical problems and 1 mark, 2 mark and 3 mark, 5 mark questions also in this chapter. In this session, I welcome you once again. Now we will take up the summary part of chapter number 5 of laws of motion. We will quickly revise what we have learned in all these chapters. Point number 1. Aristotle's view that a force is necessary to keep the body in uniform motion is wrong. A force is necessary in practice to counter the opposing force of friction. Galileo extrapolated simple observations on motion of bodies on inclined planes and arrived at the law of inertia. Newton's first law of motion is the same law rephrased thus: every body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. In simple terms, the first law is: if the external force on the body is zero, its acceleration is zero. Point number 3. Newtonian mechanics. The velocity of particle can change when the particle is acted upon by one or more forces from other object. Newtonian mechanics relates acceleration and force. Forces are vector quantities. Their magnitudes are defined in terms of acceleration. They would give the standard kilogram. A force that accelerates standard by a standard body by exactly 1 meters per second square is defined to have magnitude of 1 Newton. The direction of force is the direction of acceleration it causes. Forces are combined according to the rules of vector algebra. The net force on a body is the vector sum of all the forces. Mass. The mass of a body is the characteristics of the body that relates the body's acceleration to the force causing the acceleration. Masses are scalar quantities. Point number 6. Newton's first law. If there is no net force on the body must remain at rest. If it is initially at rest, or move in a straight line at constant speed if it is in motion. In simple terms, the first law is: if the external forces on a body is zero, its acceleration is zero. Momentum is defined as vector p is equal to m into vector v, where v is the velocity. Inertial reference frames. Reference frames in which Newtonian mechanics holds are called inertial reference frames or simply inertial frames. Ground is an inertial frame. Reference frames in which Newtonian mechanics does not hold are called non-inertial frames. Newton's second law. The net force F net on a body with a mass m is related to body's acceleration A by the relationship F is equal to ma, where F is a vector and A is an acceleration, which is also a vector, which may be written as and which can be split into x, y and z components like Fx is equal to max, Fy is equal to may, and Fz is equal to maz. The SI unit of force is 1 Newton, that is 1 kg meters per second square. Therefore, F is equal to K into dP by dt. That is differential of momentum P. That is K is equal to MA and K is equal to 1 in SI unit. Some particular forces are gravitational force Fg is equal to M into G. Weight of a body W is equal to mg. And a normal force N is always perpendicular to the surface. And a frictional force tension pulls the body on each side. Newton's third law. If a force FBC acts on a body B due to body C, then there is a force FCB on body C due to body B. The forces are equal in magnitude and opposite in direction. Therefore, FBC is equal to minus FCB. To every action, there is equal and opposite reaction. Point number 12. Law of conservation of momentum. The total momentum of an isolated system of particles is conserved. This law follows from the second and third law of motion. Point number 13. Friction. Frictional force opposes, that is impending or actual, relative motion between two surfaces in contact. Please note two surfaces in contact. It is the component of contact force along the common tangent to the surface in contact. Static friction Fs opposes the impending relative motion, whereas kinetic friction Fk opposes actual relative motion. They are independent of the area of contact and satisfy the following approximate laws. Fs, that is the static frictional force, is always less than or equal to Fs maximum, that is equal to mu s into r, where mu s is the coefficient of static friction and r is the reaction. Fk, that is kinetic friction, equals mu k into r, where mu k is the coefficient of kinetic friction. Mu s coefficient of static friction and mu k coefficient of kinetic friction are constants characteristics of the pair of surfaces in contact. It is found experimentally that mu k is always less than mu s. In this table shown on the right hand side, we will summarize the physical quantities like momentum, force, impulse, static friction and kinetic friction, clearly mentioning symbol, units, dimensions. Momentum is represented by symbol small p vector and its unit is kg meter per second or Newton seconds, and its dimension is ml t to the power of minus 1 and it is a vector quantity. Force F is unit of force is Newton and its dimensions are ml t to the power of minus 2. The net force is equal to mass into acceleration. Impulse is equal to F into t. Its unit is kg meters per second or Newton second. and its dimensions are ml t to the power of -1, and impulse is the change in momentum. Static friction is represented by symbol Fs, and it is a vector. Its unit is newtons, dimensions ml t to the power of -2, and Fs is always less than or equal to mu s into r. Kinetic friction is represented by symbol Fk, and its unit is newton, and dimensions are ml t to the power of -2, and Fk equals mu k into r. We'll continue solving problems of 2 marks and 3 mark questions in this slide. Question number 21, that is continuation of previous video on this subject. A block placed on a rough horizontal surface is pulled by a horizontal force capital F. Let small f be the force applied by the rough surface on the block. Plot a graph of friction, that is small f versus capital F, that is applied force. Answer. The graph small f, that is frictional force versus the applied force, is shown in the diagram. O is the origin and A is the first point. Up to the point A, small f is equal to capital F, that is frictional force is equal to applied force. That is, during this slope, the block is stationary, that is 0 to A, the block is stationary, and beyond A, when f is increased further, the block starts moving, that is A onward, the block starts moving and f remains constant. Question number 22. A mass of 2 kg is suspended with a thread AB. The thread CD of the same type is attached to the other end of the 2 kg mass. Lower end of the thread is pulled gradually, harder and harder in the downward direction so as to apply the force on AB. Question number 1. Which of the threads will break first? Break and why? Question 2, part 2 is what happens if the lower thread is pulled with a jerk? Answer. Part 1 is thread AB, that is this part breaks down because it is subjected to a tension which is equal to mg, mass into gravitational force, as well as the applied force. Part 2, CD will break. This one CD will break if the lower thread is pulled with a jerk. A block of mass, question 23, a block of mass m is held against a rough vertical wall by pressing it with a finger. If the coefficient of friction between the block and the wall is mu and the acceleration due to gravity is g, calculate the minimum force required to be applied by the finger to hold the block against the wall. Answer. For the block not to fall, small f should be equal to mg, where m is the mass of the block. Please see the figure here. The block is held with a finger capital F against a wall, vertical wall, and there is a downward force m into g. But f is equal to mu into r, that is mu into capital F. So mu f is equal to m into g. Therefore, the applied force is equal to m into g divided by mu. So this is the force required to hold the block against the wall. Next question, question number 24. A block of mass 500 grams is at rest on a horizontal table. What steady force is required to give the block a velocity of 200 centimeters per second in 4 seconds? So t is 4 seconds here. Answer. We have to use the formula F is equal to m into a, where F is the applied force and small m is the mass and a is the acceleration. Therefore, for the rearranging, a is equal to F by m, or a is equal to, we also know that a is equal to v minus u over t, that is equal to final velocity is 200. So 200, put the value as 200, and initial velocity is 0 because it is at rest initially, and the given time is 4 seconds. So a is equal to 200 minus 0 divided by 4, that is equal to 50 centimeters per second. We know A and we know M. We can calculate F. Therefore, force F is equal to 500 grams into 50 centimeters per second square. That is equal to 25 dynes. Question number 25. A force of 98 newtons is just required to move a mass of 45 kgs on a rough horizontal surface. Find the coefficient of friction and angle of friction. Assume G is equal to 9.8 meters per second square. So we are required to find coefficient of friction mu and angle of friction theta. Let us do it. So given F is equal to 98 newtons. Therefore R is equal to 45, that is M into G, that is equal to 45 into 9.8. That is equal to 441 newtons. Therefore, mu is equal to F by R. That is equal to F is 98 and R is 441. And substituting value of F and R, we get mu is equal to 0.22. Angle of friction theta is given by the formula. Theta is equal to tan inverse of mu, where mu is the coefficient of friction. We have found mu as 0.22. Therefore, theta is equal to tan inverse of 0.22, where if you refer the table, tan inverse of 0.22 is 12 degrees and 24 seconds. Next question. Calculate the force required to move a train of 2000 quintals up on an inclined plane of 1 in 50 with an acceleration of 2 meters per second square. The force of friction per quintal is 0.5 newtons. Let us solve it. Given force of friction, that is small f, is equal to 0.5 newtons per quintal. Therefore, total F will be equal to, total friction will be equal to 0.5 into 2000, that is 1000 newtons. And the mass of 2000 quintals has to be converted into kgs. Therefore, it becomes m is equal to 2000 into 100 kg. And sin theta is given as 1 by 50 and a is also given as 2 meters per second square. Therefore, the force required to move against the gravity is mg sin theta. Therefore, that is m is 2000, g is 9.8 and sin theta is 1 by 50. Substituting the values of m, g and sin theta, we get 39,200 newtons. That is the force against gravity. Then a force required to produce an acceleration is given by m into a. Therefore, that is equal to m, we have found 2000 into 100 kg into 2. A is 2. Therefore, that is 40,000, 400,000 newtons. Therefore, total force required is force due to friction 1000 plus force against the gravity 39,200 plus force to produce acceleration is 400,000 newtons. That is equal to 44,200 newtons. Next question. A force of 100 newtons gives a mass m1 and acceleration of 10 meters per second square and 20 meters per second square to a mass of m2. What acceleration must be given to it if both the masses are tied together? There are two separate masses m1 and m2 with different accelerations. Let us solve it. Suppose A is equal to acceleration produced if m1 and m2 are tied together and F is given as 100 Newton. Therefore, A1 and A2 be the acceleration produced in m1 and m2 respectively when they are separated. Therefore, A1 is equal to 10 meters per second square and A2 20 meters per second square. It is given. Therefore, m1 is equal to F by A1 and m2 is equal to F by A2. Substituting the values of F and A, we get m1 as 100 by 10, that is equal to 10 kg, and m2 is equal to 100 by 20, that is equal to 5 kg. Therefore, m1 plus m2 is equal to 15 kg. So, A is equal to F by m1 plus m2, that is equal to 100 divided by 10 plus 5, 15, that is equal to 6.67 meters per second. Hence, the acceleration equals of 6.67 meters per second must be given to it if both the masses are tied together. Next question. Define angle of friction and angle of repose. Please see the figure here. Small f is the friction and R is the normal, and the resultant of R and small f is shown in the red as shown in the diagram. So angle of friction may be defined as angle lambda here in the figure, which the resultant limiting friction and normal reaction makes with the normal reaction. The angle of repose or angle of sliding is defined as the angle alpha shown in the figure 2 below, alpha of the inclined plane. So this is applied, angle of sliding is applied to inclined plane only. So inclined, the angle of repose or angle of sliding is defined as the angle alpha of the inclined plane with horizontal, such that a body placed on it is just begins to slide. Next question. Question number 29. The pulley arrangement of figure A and B are identical and the mass of rope is negligible. In case A, mass M is lifted up by attaching a mass 2m. This is mass M lifted up by a mass 2m to the other end of the rope. In figure B, M is lifted up by applying a force F is equal to 2mg. In which case, the acceleration of M is more. Answer. We have to remember the formula which we derived in the previous section. A is equal to m2 minus m1 into g divided by m1 plus m2. m1 is the mass on the left hand side and m2 is the mass on the right hand side. And g is the acceleration due to gravity and a is the acceleration. Substituting here, m1 is equal to m and m2 is equal to 2m. Substituting, we get a is equal to 2m minus m divided by m plus 2m into g, that is equal to g by 3. So in first case, the acceleration is g by 3. Case B. Free body diagram of mass m is shown below. Therefore, here in case B, let the acceleration be a dash. Therefore, writing the free body diagram and the relationship m into a dash, that is force into acceleration. Force is m a dash equals t minus mg. But t is equal to 2mg. Therefore, m a dash is equal to 2mg minus mg. That is m a dash is equal to mg. Simplified. Therefore, a dash is equal to g. Hence, in case B, a dash is equal to g. In case A, acceleration is equal to g by 3. Hence, the acceleration is more in case B. Next question. Figure shows the position time graph of a particle of mass 4 kgs. What is the A? Force on the particle for t less than 0, t greater than 4 seconds and t lying between 0 and 4 seconds. Part B is calculate the impulse at t equal to 0 and t equal to 4 seconds. Consider one dimension only. The figure is shown here. Y-axis is the position and x-axis is the time scale. So 0 to 4 seconds is here, and between O and A there is a slope, and the slope is 3 by 4, that is 0.75 is the slope of the line, inclined line OA. Let us solve it. Therefore, case A, for time t less than 0, no force as the particle is at rest. For t greater than 4 seconds, that is beyond this, no force once again. Particle comes to rest. And for t lying between 0 and 4 seconds, that is 0 to 4 seconds, that is slope. As slope OA is constant, so velocity is constant and A equal to 0. So force must be 0. Now let us calculate the impulse. At t is equal to 0, impulse is given by, impulse is the change in momentum, that is equal to I is equal to mass into final velocity minus initial velocity, that is I is equal to m into v minus u. Substituting the values, m is given as 4 kgs, therefore I is equal to 4 kg into final velocity, that is the slope here, is 3 by 4 minus initial velocity here below O is, before O is 0. Therefore, simplifying, we get 4 into 0.75 minus 0. Therefore, it is equal to 3 kg meters per second. 3 kg meters per second. So, when t is equal to 4 seconds, I is equal to m into v minus u once again. But here, the initial velocity u is 0.75 and final velocity is 0 here. That is beyond 4 is 0. Therefore, substituting, we get 4 m, the value of m is 4 into 0 minus 0.75. That is equal to minus 3 kg per meter second. This is the value of impulse. Next question. Define the principle of conservation of linear momentum. Deduce the law of conservation of linear momentum from Newton's third law of motion. Let us solve it. The law of conservation of momentum states that the total momentum of an isolated system of interacting particles is conserved. Consider two bodies A and B with initial momenta PA and PB respectively. The bodies collide, get apart with final momenta P-A and P-B respectively. By second law, force of A and B, that is F of AB into delta T equals P-A minus PA, and force of B on A is, that is F of B into A into delta T equals P dash B minus PB. Here we have taken a common interval of time delta T for both the forces, that is the time for which the two bodies are in contact, that is delta T. Therefore, by third law, F of AB, FAB is equal to minus FBA. Therefore, P dash A minus PA is equal to minus of P dash B minus PB. Rearranging, we get PA plus PB equals P dash A plus P dash B, which shows that the total final momentum of isolated system equals its initial momentum. So left hand side is the initial momentum and right hand side is the final momentum. Question number 32. With the help of suitable diagram, explain the terms static friction, limiting friction and kinetic friction. Show that static friction is a self-adjusting force. Also plot the graph showing variation between applied force capital F and force of friction small f. Let us solve it. Static friction. The opposing force that comes into play when objects are at rest is the static friction. Static friction is a self-adjusting force because it changes itself in accordance with the applied force. Please see the graph above. Here, the applied force capital F is given on the x-axis. The force of friction is given on the y-axis. The static friction is between O and A. The O is the origin and A is the point. F suffix x is the static friction. It is a self-adjusting force. As the applied force increases, Fs gets adjusted and reaches a point A. Limiting friction. The maximum value of static friction up to which the body does not move is called limiting friction. That is, up to the point A, it is a point A is the limiting friction. Here, up to this point, the body does not move. The magnitude of the limiting friction between two bodies in contact is directly proportional to the normal reaction between F1 and F1 proportional to R, that is the normal, or F1 is equal to mu S into R. Direction of force of limiting friction is always opposite to that of the direction in which the body is at the verge of moving. So direction of friction force is opposing the direction of movement. Coefficient of static friction mu s is called the coefficient of static friction. Value of mu depends on the material and nature of surfaces in contact. Value of mu does not depend on the area of the contact. Third one, kinetic friction. Kinetic or dynamic friction. If the applied force sets the body in motion, the friction opposing the motion is called kinetic friction. The point from point B to C, it is the kinetic friction. It is shown in the graph here. Kinetic friction depends on normal reaction friction. That is, Fk is proportional to the reaction R, or Fk is equal to mu k into R, where mu k is called coefficient of kinetic friction. Kinetic friction is always less than the limiting friction. Therefore, Fk is less than F1 and mu k is less than mu s. Next question. Three blocks of masses M1 is equal to 10 kg and M2 is equal to 20 kg, M3 is equal to 30 kg are connected by strings on a smooth horizontal surface and pulled by a force of 60 newtons. Find the acceleration of the system and friction in the strings. The diagram is shown here, M1, M2 and M3, and the tensions are also shown. T1, T2 are shown in the figure. A is the acceleration, which is on the right side and in the direction of force. So, answer. All the blocks move with a common acceleration A under the force F is equal to 60 newtons, which is given in the question. Therefore, F is equal to, we know F is equal to M into A. Therefore, F is equal to M1 plus M2 plus M3 into A. Therefore, A is equal to F divided by M1 plus M2 plus M3 within brackets. That is equal to F is 60 divided by 10 kg plus 20 kg plus 30 kg. So, it is 60 by 60. Therefore, A is 1 meters per second. So, now we will take up free body diagram of the first block. M1 is equal to tension is T1 and A is on the right hand side. Therefore, T1 is equal to M1 into A. Therefore, we know M1 is 10 kg, M1 is 10 kg, A is 1. Therefore, T1 is equal to 10 newtons. Next, we will take up the free body diagram of M3. So, it has tension T2 on the left hand side and force, applied force F on the right hand, pointing towards right. And M3, A is the acceleration on the right hand side. Force is M3 into A. Therefore, T1 is equal to F minus T2 is equal to F right side minus T2 is equal to M3 into A. Solving, we get T2 is equal to 30 newtons. Next question. A wooden block of mass 2 kg rests on a soft horizontal floor. When an iron cylinder of mass 25 kg is placed on the top of the block, the floor yields steadily and block and the cylinder go down with an acceleration of 0.1 meters per second square. What is the action of the block on the floor before and after the floor yields? Take G is equal to 10 meters per second square. Identify the action-reaction pairs in the problem. So blocks are shown here. When blocks is rest, it is free body diagram is shown here. 20 newtons acting downwards and its reaction is vertically upwards. And another block of 25 kg cylinder is placed on it, due to which the block moves down with an acceleration of 0.1 meters per second square. So free body diagram is also shown here. Let us solve it. Block is at rest in case of A and its force is M into G, that is equal to 2 into 10. Therefore, 20 newtons. Therefore, R is vertically up. It is 20 newtons. Using third law of action of the block, that is the force exerted on the floor by the block is equal to 20 newtons and directed vertically downwards. Force is acting downwards. Question number B, part B. So now the total weight is increased by 25 kgs. Hence it becomes 25 plus 2 into 10 minus R dash, that is equal to 27 into 0.1. 0.1 is the acceleration due to movement of the block, due to which is in turn due to the weight of the cylinder. Therefore, simplifying, we get R dash is equal to 267.3. Please you work out. It becomes 25 plus 2, 270 minus R dash equals. So you can easily simplify. By third law, the action of the system on the floor is equal to 267.3 newtons vertically downwards. Action-reaction pairs. The action-reaction pair consists of mutual forces which are always equal and opposite between the bodies. Two masses of 5 kg and 3 kg are suspended with the help of massless inextensible string as shown. Calculate T1 and T2 when the system is going upwards with acceleration of 2 meters per second square. Use G is equal to 9.8 meters per second square. Please see the figure. Here, the given problem is explained in this figure. Answer. According to Newton's second law of motion, T1 minus M1 plus M2 into G equals M1 plus M2 into A. Therefore, T1 is equal to M1 plus M2 into A plus B G. That is rearranging. We get M1 plus M2 is 5 plus 3. A plus G is 2 plus 9.8, which is given in the problem. Therefore, T1 is equal to 94.4 newtons. The second body diagram, we get T2 is equal to T2 minus M2G. T2 minus M2G equals M2 into A. That is T2 equals M2 into A plus G. So we substituting, we get T2. Tension in this T2 equals 3. M2 is 3 kg into A is 2 kgs per meter square plus 9.8. So we get T2 is equal to 35.4 newtons. Next question. There are few forces acting at a point P produced by strings as shown in the figure. This point P is at rest. Find the forces F1 and F2. F1 is here and F2 is acting downwards. We have to find. And the other forces acting on P is given in the diagram. Let us solve it. Answer. Applying equilibrium condition. Sigma F is equal to 0. So let us solve. Sigma Fx should be equal to 0. That is the forces acting in x direction. Sum of forces acting in x direction should be 0. So F1 is acting along x-axis plus 1n sin 45. Sin 45, that is here it acts here in this direction. Minus 2, here it is minus 2 sin 45. So 2 sin 45 acts in direction equal to 0. Therefore, F1 is equal to sin 45. That is 2 sin 45 minus 1 sin 45 is sin 45. That is equal to 1 by root 2 n. Therefore, again applying the sum of forces in vertical direction, that is sigma Fy should be 0. Therefore, 1 cos 45, that is 1 cos 45 plus 2 cos 45, which are acting upward, should be equal to minus F2, which is acting downwards. Minus F2 should be 0, or F2 is equal to 3. 1 plus 2 is 3. 3 into cos 45 is 1 by root 2. 3 by root 2 n. That is the answer. Next question. Question number 37. A hunter has got a machine gun that can fire 50-gram bullets with a velocity of 150 meters per second. A 60 kg tiger springs at him with a velocity of 10 meters per second. How many bullets must the hunter fire into the target so as to stop him in his track? Given mass m is equal to mass of bullet is equal to 50 grams equals 0.5 kg. The mass of tiger is 60 kg. It is given here. Therefore, velocity of the bullet is 150 meters per second. Therefore, velocity of tiger is minus 10 meters per second because it is coming from opposite direction. N is equal to number of bullets per second at tiger so as to stop him. Therefore, Pi, that is momentum, initial momentum should be equal to 0 before firing. Pf is the final momentum, that is equal to N into mv plus m into v. That is small n is the number of bullets and small m is the weight of the bullet. So from the law of conservation of momentum, Pi is equal to Pf. Therefore, 0 is equal to n into mv plus capital MV, that is equal to n of capital MV divided by small mv. Therefore, that is equal to minus 60 into minus 10 divided by 0.05 into 150. That is equal to answer is 80. Next question. Two blocks of mass m, mass 2 kg and 5 kg are connected by an ideal string passing over a pulley. The block of mass 2 kg is free to slide on the surface inclined at an angle of 30 degrees with the horizontal, 30 degrees with the horizontal, whereas 5 kg block hangs freely. Find the acceleration of the system and tension in the string. The given problem is shown in the diagram here. We have to draw. I think he has not given. We have to draw this. Incline, the angle of inclination, 5 kg mass and the 2 kg mass. Let us solve it. Let A be the acceleration of the system and T be the tension in the string as shown in the figure. Equations of motions for 5 kg and 2 kg blocks are 5g minus t equals 5a and t minus 2g into sine theta minus f equals 2a, where small f is the frictional force or force of limiting friction. Therefore, that is equal to small f is equal to mu into r, mu into mg cos theta. Therefore, mu is given as 0.3. Coefficient friction is 0.3 into mg is 2g into cos 30. Solving 1 and 2, we get A is equal to 4.87 meters per second square and T is equal to 24.6. Question number 39. A monkey of mass 40 kg climbs on a rope which can stand at a maximum tension of 600 newtons. In which of the following case will the rope break? That is, the monkey climbs up with an acceleration of 6 meters per second square. Case B climbs down with an acceleration of 4 meters per second square. Part C is climbs up with uniform speed of 5 meters per second. D falls down the rope nearly freely under gravity. Ignore the mass of rope. Here, the monkey is shown as climbing up and down. We have to solve 4 different cases. Case A, M given. M is equal to 40 kg and tension maximum is equal to 600 newtons. Therefore, tension in the rope is equal to apparent weight of the monkey, R. So, the rope will break when R is greater than T. Therefore, case A, when the monkey climbs up, A is equal to 6 meters per second. It is given per second square. And R is equal to m into g plus a. Therefore, that is R is equal to 40 into 10 plus 6, that is equal to 640, which is greater than T. T is 600. So, the rope will break because the apparent tension reaction is more than T. Part B. When the monkey climbs down, A is equal to 4 meters per second. Therefore, R is equal to m into g minus a. Therefore, this is R is equal to 40 into 10 minus 4. That is equal to 240 newtons. So, R is less than T. Hence, rope will not break. Part C. When the monkey climbs a uniform speed of 5 meters per second, A is equal to 0 because uniform speed. There is no variation in speed. Hence, A is 0. Therefore, R is equal to m into g minus 0. Therefore, R will be is equal to 400 newtons, which is less than T, hence rope will not break. Case D. When the monkey falls down the rope freely under gravity, A is equal to G. So R is equal to m into g minus g. Therefore, that is equal to 0. Hence, the rope will not break. Next question. Question 40. A hockey player is moving northwards and suddenly turns westwards with the same speed to avoid an opponent. Find the direction of the force that acts on the player. Please see the diagram is shown here. North, south, east, west is shown here. And a hockey player is moving northwards and suddenly turns westwards with the same speed to avoid an opponent. Find the direction of the force. Hence, the diagram is shown. From the figure as shown above, OA is equal to P1, momentum P1, initial momentum of the player northwards, OA, and OB is equals P2, final momentum of the player northwards, that is final momentum of the player westwards. And OA plus AB is equal to OB. Therefore, AB is equal to OB minus OA. That is, OB is P2 minus P1. P1 that is equal to change in momentum. Therefore, change in momentum is along the southwest direction. That is the answer. As the motion is due to the frictional force of the reaction of the ground, therefore the force that acts on the player is the frictional force along the southwest direction. With this, we come to the conclusion of some of our work examples. More problems will be taken when we solve the model question papers and other things. In the next session, we'll start with a new chapter, chapter number 6, that is work, energy and power. Till then, goodbye.